Thanks for the introduction, and thanks to the organizers for the opportunity to present my work here today. So, we introduce a new architecture called Dynamics, where we try to follow the trend in large language models to generalize to new tasks using contextual information. So, a bit first to the task setting. So the most temporally evolving phenomenon like climate dynamics or brain activity can be described by dynamical systems. And often we only observe some data from these dynamical systems. And what we want to do is to build a generative model that can infer the properties of these dynamical systems from this observational data, and such that I can generate the dynamical system, including its invariant properties, its invariant long-term properties like the geometrical agreement of the attractor, as well as the temporal agreement between the power spectra of the ground truth system, as well as the generated system. Okay. So the major point in this is that most of these approaches require task-specific training. So you have a specific model for each dynamical system. And we, based on the observations in large language models, which can generalize to new unseen tasks just by providing some context information, we ask the question, okay, can we make this work for dynamical systems reconstruction? So for that, we just sampled some pre-training data, so basically lots of different dynamical systems. And the idea is that we put this into a foundation model and basically pre-train the foundation model on all of this data, such that after training, I can just provide some context trajectory, some short context trajectory of this dynamical system, and put it into my foundation model as a context, and then it should be able to reconstruct the dynamical system, including its invariant long-term properties. So there has been work done to achieve this. So what people did is they took large language models and trained them on a lot of time series data, which then resulted in time series foundation models. And when applying these time series foundation models onto dynamical systems, we often can see that they fail dynamical systems reconstruction. As you can see here, the attractor geometry is not well matched, as well as power spectrum and the individual dimensions are not accurately forecasted. So therefore, we introduce dynamics, which is based on a mixture of experts architecture using recurrent neural networks. So what we are doing is we take a bunch of recurrent neural networks, which are in this case the recently introduced almost linear recurrent neural networks. And what we are doing is we are feeding the latent state into all of these RNNs, and each of these RNN is predicting a next latent state. Then we weight these latent states by some weighting, which then gets aggregated into the next predicted latent time step, from where on we can, using an observation model, produce our observation outputs, and then autoregressively we can feed back into the signal into these RNNs again. So, and in order to calculate these weightings of the RNNs, we use a gating network that acts based on the context. So we input the context as the time series into this network, which consists of an CNN encoder and as well as a state attention mechanism that processes this context and then puts all this together into a feed-forward neural network, which then predicts my weightings. So training is done like standard in dynamical systems reconstruction. So we train using backpropagation through time based on the mean squared error loss between the ground truth and predicted trajectory. Furthermore, we employ a sparse teacher forcing protocol, which recalibrates the trajectory or the latent states during training to tackle the exploding vanishing gradient problem. And overall, we train on 0.6 million trajectories sampled from 34 different dynamical systems. Where we basically take the first few time steps as a context signal and then make the predictions on the last few. So to get to the results, we can see that with this kind of approach, we are able to zero-shot forecast unseen dynamical systems, unseen chaotic dynamical systems. So here we just provide this gray time series as a context to the model and are able to accurately predict the correct state space behavior as well as power spectrum. Furthermore, we are able to generalize to new initial conditions. Since we're dealing with RNNs, we can initialize them at different initial conditions in state space, and we can see that even though here the gray is again the context, so we can also correctly forecast trajectories outside of the context domain. Furthermore, we can see that we get good dynamical systems reconstruction only based on a few hundred time steps, which are often sufficient to reconstruct the attractor. And furthermore, since we're dealing with dynamical systems, we can sample them at different temporal resolutions, and we can see that our model can work robustly across some temporal range. So here are a bunch of examples from zero-shot forecasts using our architecture. So we can see that all of these dynamical systems, which are completely unseen during training, and we just provide a short context window, can see that most of them can be correctly forecasted. And since we're here in a zero-shot approach, this can be done within a few seconds. Yeah, so it's also quite efficient. And when we now compare the performance to the time series foundation models, which are already out there, we can see that in terms of long-term measures, we outperform basically all the other time series foundation models, which are shown here in gray. And as well as in the short-term prediction error for which these time series foundation models are actually designed for, we can see we can match the performance here. So, and furthermore, we are also highly efficient in terms of parameters as well as inference time. So you can see that a lot of these models have millions of parameters and also take a lot of time for their inference, whereas they're highly efficient. So then we ask the question, okay, why are these foundation models failing dynamical systems reconstruction? So first of all, they often only forecast univertly, so they cannot account for correlations between dimensions, and therefore one can get this kind of dimension misalignment. Furthermore, they suffer from long-term failure, where dynamics either converge to some fixed points or some cyclic behavior, some wrong cyclic behavior. And especially in transformer-based architectures, one often has this context parroting mechanism where the transformer-based model just copy-pastes the context, right? And especially this, due to this context parroting mechanism, these models are unable to predict chaotic behavior, as you can see here. So Since we're just copy pasting the context, we basically get some cyclic behavior in our dynamics, which then results in high peaks within the power spectrum. Whereas for chaotic signals, one should get kind of a smoothed out power spectrum, which we can match using dynamics. And when calculating the Lyapunov exponent, the maximum Lyapunov exponent, which kind of quantifies the chaoticity in this dynamical system, we can see we can quite good match the ground truth, whereas time series foundation models like here Kronos, for example, get a maximum Lyapunov exponent close to 0, showing that this is cyclic behavior. So furthermore, we can apply this architecture to time series forecasting. So we have a 1D dynamic 1D time series. So what we can do is we can delay embed it or embed it into a dynamical systems, either via delay embedding, or here we also propose some positional encoding mechanisms similar like in transformers. And what you can see is that with this approach, we are also able to accurately forecast real-world time series data from traffic data to weather data, also to medical data here. And this shows that we can compete in this zero-shot forecasting with these time series foundation models, as well as this shows that dynamical systems-based principles bear great potential for the field of time series prediction. So for future work, so we are trying to kind of extend the context information to the model, where we currently just provide some historical time series data here. But now what we want to do is also to include some external input, either via some textual context, which then can get processed through a large language model. And we then can combine these two predictions into a combined prediction, making it able to account for external information. Furthermore, we want to expand the training corpus and the model architecture, because currently we are mainly focused on rather stationary time series or dynamical systems. And as you can see, the model then will struggle to predict non-stationarities. However, when adapting the model architecture using some decomposition modules like done in autoformers or fedformers, we can see that also then with the dynamics we can fit this non-stationary data. So with this, feel free to take a look at the paper or check or play around with the model actually at our interactive Hugging Face hub. So there you can just play a bit around with it. And with that, I want to thank my supervisor, Daniel Dustewitz, for supporting my work, and thanks for your attention.